Happy afternoon. The next speaker to present here on the topic of food product design for microwave heating is Dr. Ramaswamy C. Anantheswaran. I'm very happy to introduce you, sir. Dr. Ramaswamy Anantheswaran is a professor of food engineering and the director of education at Pennsylvania State University. His research interests include microwavable food product development and processing, chocolate and confectionery processing, modified atmosphere packaging of fresh produce, high pressure processing of foods, and food process modeling. He serves as the chair of the Cocoa Chocolate Confectionery Research Group at Pennsylvania State University. He has authored over 130 publications and the Handbook of Microwave Technology for Food Applications. He is a visiting professor at IIT Bombay and serves as the consultant to several food companies both in India and USA. Sir, I welcome you for the presentation. Please give a big round of applause.
Good afternoon, and I have to thank Gustavo because he already talked about one of the applications of microwave heating. And what I want to do is, he would agree the microwaves heat the food product very differently than conventional heating. So if you are developing a commercial process using microwaves, you have to understand how it heats up. And if you are developing products for the processed food markets, you also have to understand how the products heat. So back in the good old days, 20 years ago, when everything came up, back in the US at least, the same product formulation for conventional heating was used in the microwave heating, but people never came back because quality is still important. Since microwaves heat the products very differently, the final cooking and the final temperatures, final quality is very different. So it's like the joke I use is, you use a bread toaster for toasting an oven, but you don't use it for poaching an egg, right? You still heat. So again, need to kind of have you think a little bit about, from an engineering design standpoint, the interaction between microwaves and food products, things you need to keep in mind if you're working for ITC, working for Naga Foods, working for Unilever, or if you're a company developing microwave equipment for use in microwave assisted thermal processing or microwave drying, and a whole host of processes that you can develop for food manufacturing. So again, I have to tell you, the theme of the conference is doubling farmers' income through food processing. It's ironic that on Monday at 3:30 to 4 o'clock, I'm giving a talk at IIT Bombay to engineers and scientists and professors. How do you use science and engineering to develop innovative technologies for food and agriculture? And one of the things that we are doing there is a thing called a Tata Center. The Tata Trust has given them about 250 crores to go and make a difference in the rural areas. So one of the things I'm helping them is, why not take the chemical engineers, teach them about the unit operations? Why not take mechanical engineers, teach them about harvesting, and use the same technology? So we are doing, a lot of things that we heard Padma Singh talk about, empower the farmers by helping them add value. I'm talking about that there, but then somehow I felt what would be more appropriate for this audience here in the Institute of Food Processing Technology is teach them the do's and don'ts about microwave heating. But I'll be glad to talk about where I think some of those technologies can also be used to add value to some of the products by farmers here in India. So this is a well-known fact. Food companies are coming like crazy to India because US is not growing, Europe is not growing. The countries that are growing in terms of middle class income going up is India and China. Used to be BRIC, Brazil, Russia, India and China. Brazil has gone off the map, Russia has gone off the map. It's India and China that everybody eyeing for a market share. So again, there is places like Mumbai, Delhi, Chennai. The opportunity for processed food market is tremendous. Whether it is consumers or even where you need that quick menu to be delivered. And again, you need this wanted to say was these technology, microwave heating, like a high temperature, short time process, as my friend Gustavo showed, the processed eggs using microwaves as compared to conventional sterilization, the quality was better. So all of the products heated in microwave, if done right, it can be much better product quality than conventional heating. And again, a much better nutrient retention, and also you don't waste a lot of energy using microwaves. It's quick heating, you don't heat the entire, and also it's a green technology. Very little of the product is just used up. So again, here is a schematic of a microwave oven. Similar technology is used for commercial oven. This is an industrial oven. You have micro generator, a magnetron exports it to a waveguide, and the microwaves are incident in what's known as the. Then the microwaves come from all different sides, and sometimes you even have a false bottom in a microwave oven so that microwaves can reflect from the bottom of the particular false bottom and come into the food product. So this is what so typical wave mechanics takes place. You have reflection, you have penetration, and then again you have some absorbance going on in microwave heating. So this is similar to the equipment that Dr. Canova showed us. It's an industrial microwave oven for heating of food products. Similar ovens are available for sanitation, drying, so on and so forth. The nice thing about industrial ovens is you can control the uniformity of heating much better in an industrial oven. Cost is not, but a consumer microwave oven, you still get non-uniformity because you have a lot of reflection taking place, and control of the microwave power is difficult. You have good microwave ovens available for $450, but the price point seems to be somewhere about $150 in the US market, so it becomes challenging. Whereas in Europe, they have a combination of microwave and quartz heating element, which gives some advantages, which I will talk about shortly. So again, microwaves heat. People think microwaves are athermal. No, it's not athermal. Product composition. The water in a food product is what absorbs microwaves. The dipole molecule rotates the long frequency, and that rotation in that viscous matrix causes friction. So it's again microwaves resulting in this friction or the rotation of the water dipole, which then results in friction leading to thermal energy. So again, these are all the factors in a consumer oven that will affect the uniformity. The bigger the size, more the non-uniformity. Smaller the oven, they are more uniform because of the reflection along the things. And again, geometry. In Japan, I've seen a spherical oven because spherical oven actually kind of uniformly distributes compared to a box type of oven. But again, 99% of the ovens sold in worldwide is a box type of oven. The distribution of electric field depends on how many waveguides you have, whether you have waveguides coming from the sides or is it coming in the top. Do you have a mode stirrer? Then again, in a bigger oven, you have a turntable, and product moving in that turntable takes away from that non-uniformity. Then you have mode stirrers, that's that thing on the top. Some of the older ovens used to have that, the metal fan, which used to distribute a microwave oven. Then the location, orientation, number of power feed ports. The newer Panasonic ovens have more than 2 entry points, which sort of makes that waveguide look treated as a more uniform. Then again, where you put the product in that microwave oven is going to make a difference. So the microwave power incident in the product will be different in the center, different on the back. So as a product development scientist in a company, you need to take into account where you're going to tell your particular consumer to put the product. Then again, power output, standing time. A lot of times, the best thing to get rid of that non-uniformity in microwave is, at the end of the microwave heating, let the product stand for 30 minutes, let conduction heat transfer equilibrate. Let's take advantage of physics to our advantage. We don't need the product to be eaten. We can afford to give up 30 seconds for the sake of uniformity. So again, there are ways to kind of do that. Then I mentioned about the auxiliary quartz heating element that's used in a lot of the European ovens. So if you freeze the pizza, you can thaw the pizza quickly in a matter of 3 minutes using microwaves. But cooking a pizza to get that crisping is very difficult to do in microwave. You can use a quartz element to do that. A lot of us, what we do in US is we will thaw the pizza slice in a microwave, then put it in a tabletop toaster oven to kind of heat it. The kitchen square feet in Europe is a premium, unlike in US, so they have more of compact ovens and things of that kind. So from a product standpoint, also the shape of the product makes a difference. If it is a cylindrical product, it will have center heating. If it's a rectangular product like a slab, it will have corner heating. And if it's a spherical product like a pea, it will have center heating, because that's how the waves travel within the food product. The formulation of the product is going to make a big difference. If water is the major component, you don't have to worry. The water is basically, we know the dielectric properties, dielectric laws. But even if that water of the food products has 0.01% salt, the salt is going to contribute to that heating due to polarization. 0.1% difference in salt concentration can totally change the heating profile in food products. This is a consideration for companies like Campbell who make soup products. They need to standardize the particular salt concentration much, much more stringently than what they do for sensory characteristics, because it affects their rate of heating in the microwave. Then, of course, you have that free water versus bound water concept. That's going to make a difference. So if you have 0.1% guar gum versus 0.5% guar gum, your particular amount of water available for some of the dielectric interaction is going to change. And of course, things like emulsifiers, charged molecules will all affect, because chargers interact with microwaves very differently than the water dipole molecule. Of course, temperature is just like any other food property. Temperature is going to affect basically the heating property, and the two electrical properties that we are looking to characterize to understand microwave heating, the dielectric constant and the electric loss factor, and you measure it using a piece of equipment called network analyzer, which any electrical engineering lab has. So if you want to understand microwave heating, you need to understand, think like an electrical engineer for the interaction, to talk like a mechanical engineer to talk about the heat transfer. Then you need to think like a food chemist to understand the effect of heating on the interaction between the proteins, and the biology also comes into play, because if a product that is sterilized, you also need to know what the temperature profile is and the resultant microbial destruction is. And again, conversion could take place during thawing in a lot of the starch-based products. You need to keep that in mind, especially if you're freezing a product and then bringing it back and heating it in microwave. And of course, one of the important challenges, I'm using an electrical engineering term, impedance matching. You're designing a speaker for a sound system. You have to match the speaker with the power coming from the amplifier. And this is the same system. You have the microwaves coming in, that particular energy is being absorbed by the product, and the impedance of the product, which is a combination of the electrical resistance and the capacitance, is to match. So you have to design the food product. You have to choose the composition, so you design that size value of electrical impedance into the food product. You can use the help of the package to be able to match it. Of course, the type of the package, that's a lecture by itself. There are lots of technologies available. I was talking to one of the gentlemen here about microwave heating of popcorn. The way they heat it up is put up electrical susceptor, and susceptor package is like a metal griddle. It's a micron layer thick metal put into a plastic material so that the electrical conductivity is altered so that the temperature is heated up so the microwave popcorn can pop, and you get much higher pop ratio in a microwave oven. So the susceptor package that's used for microwave popcorn and for pizza, French fries is done to improve the temperature of the particular heating. Otherwise, for all practical purposes, all microwave does is just a steaming. But steaming is not enough for popping. Steaming is not enough for crisping a pizza. Steaming is not enough for browning reaction. So if you want browning reaction, improved popping performance, crisping, all of those reactions requires you use a electrical susceptor within the package. So again, advantages I'm going to skip because it's very similar to what Gustavo said in terms of microwave assisted. These are some of the things. The disadvantage is very, very big disadvantage. If I use 2 minutes to heat 1 cup of water, 4 minutes is not what you use for 2 cups of water. That particular loading ratio changes. So having a sort of a regulatory sort of a thing, you can't set the temperature, whereas you need temperature at the set point for a lot of the microwave, rather traditional cooking. So coming up with that is difficult. We need sensors to be able to look at the product quality, and the microwave ovens have those sensors built into it. Crisping doesn't take place because, like I said, microwaves mostly act like a steamer, and crisping can take place if you put a susceptor in the bottom of the package. Browning does not take place because during steaming, the temperature only goes to 100. We need temperatures above 120 degrees Celsius for browning reactions to take place. And of course, the biggest problem is uneven heating, and my biggest solution for that is let the product stand for a couple of minutes or maybe at least 30 seconds to equilibrate the temperature. One of the solutions is never heat the product at full power. Always heat the product at half power so you don't get burn spots and other things. So again, when Gustavo said we cook a product, to be honest with you, when my wife visits India for 3 months, I literally live off on microwave because I know how to use it. I cook rice in a microwave, I cook vegetables, I can do literally anything I want if I understand what a microwave is capable of doing and not capable of doing. So again, it's a good cooking device, but you have to use it differently than a and differently than an oven that you use for a lot of the baking operations. So again, this is another tube, load versus power output. So again, when you put a small amount of product, so it is a 1000-watt oven, a small amount of product, surface area is minimal, it doesn't absorb 1000 watts. The microwave enters the food product from the surface, so more the surface area, more the absorption of microwave power. So smaller products will absorb less power, larger products, because of the larger surface area, will absorb. So you need to characterize what's known as a power absorbed versus the amount of load. You need to know what the loading curve is to take advantage of the entire power that's coming from the microwave. So larger the cavity size, less the power is absorbed. So basically what they are saying is you need a product that fills up the particular oven if you want to take advantage of the entire particular. If you buy a 2500 watt microwave oven and if you put a cup of water to heat, it's not going to absorb the 2500 watts. It's probably going to absorb 500 to 750 watts. You're better off by 700 watt oven. You're not going to use it for larger amount of food products. So again, this is now electrical engineer. If you know what the properties are, epsilon prime is the dielectric constant, tan delta is the ratio of dielectric constant to dielectric loss. You can determine what's known as the Z parameter or the Z parameter, which is the penetration depth. The calculation of Z tells you the depth in the material at which 37% of the surface value of electrical field is absorbed. So you need that particular, the penetration depth to be about 1/3 of the thickness of the product. And also the penetration depth constant is in a lot of the modeling studies that 1/Z, the penetration depth is alpha, that attenuation factor. Then we use the Beer law to look at the perpetuation or the propagation of microwave in the food products to do electrical modeling and then subsequent heat and mass transfer modeling using any of the traditional packages. Again, when you're doing product testing, you have to measure temperature. You can't use thermocouples, metals arc, short metal arc within a microwave oven. So you need what's known as a fluoro-optic temperature probe. It's basically a fiber optic probe. The tip of it has a material which responds to temperature. And again, the only problem is thermocouple probe is only about $20, whereas a fluoro-optic temperature probe is about $400. But you should measure the temperature then of heating if you are in the product development operation in a company, because you should know what the temperature the product reaches in the range of microwave ovens that the consumer uses. So again, this is what that fluoro-optic temperature probe looks inside a microwave oven. We have done a lot of studies in modeling, and we would always validate our model with temperature data and then validate microwave absorption. So again, now switching from theory to practical, develop foods for microwave oven is difficult. You need to understand the electrical engineering part. You need to understand the mechanical engineering part, the food science, but the rewards are there. And again, I want to tell you about these novel microwave ovens in the European market, the quartz elements, and then again there is a combination oven which is about $450 in the US. So you can heat up using microwaves. Then you also have hot air heating up the product, so you can thaw the pizza and crisp the pizza in the same microwave oven. Sharp and a whole bunch of companies sell them to the select group of people in the niche market area. And again, there are lots of sensors. With sensors, it can measure the number of pops in a microwave, number of pops of popcorn, so it will shut off before the microwave popcorn burns. It can measure the amount of humidity, so it knows when the product is completely cooked. And they have ovens with basically UPC codes, so that if you scan the product, it knows what the product is, it knows what the weight of the product is. They have pre-programmed the heating cycle for the product based on that. So a lot of technology exists, but again, combining it to some practical ideas takes some understanding of the marketplace. So these are some of the metallized film receptors. That's a separate technology I talked about. Is basically aluminized metallized polyester film, and again, you use this to get the temperature above steaming temperatures in a microwave oven. So it's part of the microwave packaging technology. There are wonderful, wonderful technology. This used to be a company from Canada, Alcan, aluminum company of Canada, that had developed this particular grading technology to control the amount of microwaves into an entree where you want the meat product to heat differently than the vegetable product and compared to some of the potato products. So using grading technology, they were able to control the amount of microwaves. And again, some of the problem with the technology is the cost of this particular package becomes more than the particular food cost. So again, technology, but too ahead of its time, even for use in the US and the Canadian market. You should always test your product for abuse by the consumer, because consumers can always find a way to kind of abuse the product, not use the direction. The most important thing is you don't want to cause fires, you don't want to cause sparks. So again, the instruction should be robust, in that if consumers should still come out to be a better product. So product abuse testing is highly recommended, and you need to do this product performance testing in a whole range of oven, anywhere from 450 watt to 2000 watts, using particular manufacturers. Again, you need to understand the entire heat transfer part. Okay, thank you. So you need to understand the mechanical engineering part. You need to understand what happens to the product during thawing. And again, ice absorbs microwaves very differently than liquid water. So you need to understand the dielectric properties of ice are very different than the dielectric properties of unfrozen water. You need to keep into account, take that into account. If you're developing a product that is frozen, it's going to be heated in the microwave, because ice is going to absorb 1/10 of the energy, then once it thaws, it's going to absorb 10 times more energy. So you need to keep that in the back. And again, you need to understand how the temperature mediated gelatinization takes place, how the polymerization of proteins takes place, and all of the qualitative aspects of flavor development. And again, starch selection is very, very, very important. Companies such as Ingredion has developed a customized range of starch for use for product development for microwave ovens. And again, you can define products, but again, comes back to understanding the electrical engineering, the microwave interaction of these particular products. And again, especially for developing product instructions for microwave for frozen food products, you need to basically have much better cleaning directions so that the consumers don't get basically abuse the product. So just want to quickly take 2 minutes to talk about some of the projects that we have done at Penn State. So one of the things we did was try to understand how do you develop microwavable popcorn. What we found, I was working with a breeder at the University of Nebraska. Microwave popping is very different than commercial popping. There are a couple of publications of mine, you can look at it. We found we need a different variety of popcorn for microwave popcorn, and then a variety of popcorn that works well in basically the conventional popping arrangements. The location of the water, location of the endosperm, all makes a big difference, and what works for conventional popping we have basically modeled the convection heating, temperature distribution during convection heating of product with an intent of coming up with microwavable heating of microwave sterilization of products that are going to be heated in microwave. So we did all the thermal profile, and the bottom analysis is when you have these plastic containers, they usually put a metal seal on the top. The metal shield is actually because it shields the microwave from coming in, and it actually promotes much better convection in these products. Otherwise, the microwaves coming from the top arrest the convection heating of this product. So we have worked with manufacturers to design the package based on our modeling studies. We have looked at, there was this great controversy, the microwave skilling, or is it the temperature produced by the microwave? We showed with the study in destruction of Listeria monocytogenes, where we were control the temperature, that the entire killing of microorganisms, the Listeria, is due to temperature mediated. There is no thermal effect. You need temperatures up to basically 800, 900 degrees centigrade, which happens in ceramic industry, for some of those non-thermal reactions to take place. And again, microwaves can also be used as a sensor. The dielectric properties change with quality, dielectric properties change with particular composition. And this is a company, the guided microwave spectrometer, very similar to what you talked about, Digveer. They use this hyperspectroscopy, sort of a kind of a measurement. They look at the property of the material in the microwave range, and from that they can infer the salt concentration. They can infer how much the bound water is, how much the free water is. So these things are used by confectionery industry, used by the pasta industry, while they formulate the product to control the moisture distribution, to control the amount of cocoa butter, to control the amount of moisture, things of that kind. particular area. Again, small little concentration differences in salt up to 0.1%, you can pick it up using this microwave spectroscopy. And again, lots of application with the food industry, kind of chimes with what Gustavo was trying to tell us. I'm going to stop right here and see if you have any questions.
Yeah. Thank you, Dr. Ramaswamy, Anantheswaran, for a wonderful, I would say, a sort of awakening amongst all of us, especially how to use the microwave and what are the I would say, the parameters that need to be considered and how it can be used in the food applications. I think that was a very great, I would say, scientific insight into the microwave utility for food processing. So thank you very much, sir. I think you have covered almost everything what is supposed to be, and it's a good lesson for every one of us, because we always feel microwave is important for the home, but we don't know the applications. Probably these are the ways we can really understand the applications and bring in this into food science. That's where I think you have really awakened us. So thank you very much for an excellent presentation. Thank you, sir.
The speaker
Excuse me,
with
sir.
shawl and memento.
Sir, I have one question. Please. Only single question. Okay. First of all, thank you, sir, for your knowledgeable lecture. Sir, I have one doubt that there will be the nutritional loss in that any food. It may be fish or it may be any food. So, which nutrients will be more affected, and what will be the principle behind that?
See, my hypothesis, not hypothesis, my sort of answer is, what is destroying the nutrients is time and temperature. And I submit to you, microwave heating is a high temperature short time process. Microwave heating is a high temperature short time process. Knowing what that D and Z value of the nutrients, with the reaction rate for destruction of nutrients and activation energy, a high temperature short time will always result in much less destruction of nutrients than conventional heating. So if you buy into that kinetic argument, microwave heating, if done properly, will always have much better nutrients. And also, a lot of times we lose nutrients in that water that we use for heating of food products, then we throw the water away. So we lose not only due to temperature mediated, we also get leaching of nutrients, whereas I can heat a product in the same moisture the product has. You don't need to have any water that you need to throw away. So again, from a nutritional perspective, microwaves, if we do for blanching in home, canning and stuff, much better, much more nutritious product than conventional heating.
No, I think if I can throw some light on your question, probably. It's only an intervention. In fact, any cooling or reheating, recooling will have an impact on the status of the food. Probably that is the reason why we always say food which is frozen should not, once it is thawed, should not be refrozen. So that means there is a nutrient loss always. So that nutrient loss could be because of various parameters. Probably they mentioned the sense. I think that probably you would have understood. Years to come, we may need a computer along with a microwave to arrange, to fix up the what you call the parameters of heating as well. So that will definitely take care of the food quality. That's what is the science which I feel will be with us maybe in years to come.
Sir, thing is that in case of like the freezing or canning, in case of the freezing, there will be the protein denaturation because of the very low temperature. In case of the canning, there will be the protein denaturation as well as the lipid oxidation at the very high temperature. So in case of that that microwave oven, in both protein or lipid, in both which nutrients will be more affected, sir?
No, that's what. No, it has the nutrient profile which could impact especially on the fats. Could be, there could be protein denaturation. So all these things will be, it's a complicated thing, and we need to study all that. As I said rightly, but probably we need to have a computer to fix these and these parameters can be taken care at this time. That's all. So
Thank
that's
you,
what, that will give you the clear answer. Yeah.
Thank
Uh,
you.
You know,
the
maybe I can talk to you one-on-one.
audience-
You can discuss with
Thank you, sir.
Professor
Thank
It's
you.
a
Ramaswamy
humble
later on.
request. The audience can
Yeah,
talk with the speakers
Yeah.
during lunch and dinner time and others free time.
Yeah,
Please,
good.
time is, we are running short of time.
Yeah, probably I think let us close this, the Golden Jubilee Series 2, and giving him a big round of applause for all his efforts. Thank you.
Now I request the chairman to felicitate the speaker with the shawl and memento.
See, every time I come to Tanjavur, I go to the palace store or to Pumbahar. This time I have to buy 1 or 2 because I don't have too much room. Thank you.
Sir, actually this model we have done exclusively, where is the model? Actually we wanted to create a structure in front of the institute. If you probably, this is the first food processing what we have seen it, hand pound rice. Because this institute started with the paddy processing. That lady, what processing the hand pound rice. Still, what we polished rice does not have the bran and fiber is missing. So we wanted to symbolically make it, already structure has been made 25 feet height with the waste material generated by the IIFPT. But because of yesterday incident, we could not erect that structure in front of that. Possibly another 10 days time we can do that. The same structure, we made it for Golden Jubilee structure. We are going to give all the speakers. Thank you very much, sir. You may be loud at this one.